Hello, it's time for a lesson on gas stoichiometry. And don't worry, it's not really much different from any other stoichiometry that you have learned in the past. There's just a few extra little things I have to tell you about. So, this looks a little bit confusing right now, but it's really not. I just wanted to have the flowchart that we have used in the past kind of in front of you so I could reference it. So if you look here, you'll see that the key to stoichiometry is the mole-to-mole conversion, which is in the center here. And your goal is to get whatever unit you're given in the problem converted into moles of X. And then you can use the mole ratio to take moles of X to moles of Y. And you have to convert back out to whatever they ask for in the problem. So that hasn't changed. And so I'm just going to show you a couple problems and then tell you what is different. So you can see here in the equation that it's balanced. It's got the coefficients that it needs. And you notice that there are G's in parentheses after both the reactants and the product. So we have some gaseous substances that we're working with. Okay, so step one in stoichiometry is always to start with the balanced equation. We have that. Check. And then we need to identify what value we've been given and what value we're being asked for. So let's read this first problem here. What volume of nitrogen at STP is needed? That is what is being asked for. And then it is reacting with 57 milliliters of hydrogen at STP. So that is what is the given. So hydrogen is given. And what volume of nitrogen is what's being asked for. So I'm going to label this Y and this X. Okay, now we're going to start with what we know about X, which is that we have 57 milliliters of it. So we have to, actually, what I would do first is kind of lay out your plan here. So if you have 57 milliliters of X, you're going to have to get that converted into moles of X, and then moles of Y. And then what are they asking for? What volume of nitrogen? So that's going to be liters again. Or you could put it in milliliters if they ask for it, but I would just solve for liters. Okay, so there's our plan. Now before, when we did stoichiometry, in my class in Chem 1, we did a little bit with volumes of gases, but I don't think that Mr. Griffiths' people have. So let's look back up here at the flowchart. So what do you do if you're given liters? Well, if you were given mass, you know what you do. You look on the periodic table and get the molar mass, and that helps you convert to moles. Or if you were given particles like atoms or molecules, you use Avogadro's number to convert. But when you're given liters, there's two things you can do. First of all, if you're at standard temperature and pressure, there is a conversion factor that's always true. 1 mole of gas takes up 22.4 liters of space. So let's look at the problem. Are we at STP? Yes, we are at STP at the beginning, and we are at STP at the end. So that's important to label the conditions. So the conditions don't change, and they are standard temperature and pressure the whole time. Okay, so I can use this conversion factor right here to get from liters at STP into moles. Then I'm going to have to use the mole ratio to jump across moles of X to moles of Y. And then how do I convert back to liters? Well, if I'm at standard temperature and pressure, I can use the 22.4 liters per mole again. And notice this time it's just flipped upside down because you're converting back. Okay, now, what's going to happen if I use, let's see, 1 mole has 22.4 liters at the beginning, and I have my mole ratio in the middle, and then at the end I have 22.4 liters makes 1 mole. Can you see what's going to happen there? Those two are going to cancel each other. So that leads to something interesting, and it is right here. if the conditions don't change from the beginning of the problem to the end of the problem, you really don't need to use that first conversion factor to get to moles and then that same conversion factor to get back out for moles, because they're going to cancel each other. All you really need is the middle conversion factor, which is the mole ratio. That they call it, well, I have it labeled up here. It's a shortcut you can use only if the conditions don't change. So that means it was standard temperature and pressure beginning and at the end. It would also be true if it was some other set of conditions at the beginning and end, like if it was 5 atmospheres of pressure before and after, and the temperature stayed constant. It doesn't matter what the conditions are. If they don't change, you really only need one conversion factor, which is this middle one. Okay, I'm going to erase this because I don't want it to be overwhelming, all this crap up here. Okay, so I'm going to take away the need to convert to moles and the need to convert out of moles, and I'm just going to use that middle conversion factor. So I have 57.0 milliliters of X given, and I'm going to write the mole ratio in the middle. There are 3 moles of X for every 1 mole of Y. Now, the thing is, moles are not going to cancel in milliliters. And so what you do in this kind of problem when the conditions don't change is instead of using moles in your mole ratio, you actually use milliliters, or whatever the volume unit was. So that milliliters can cancel milliliters. And you're left with milliliters. So this 1 to 3 ratio right here is basically the mole ratio, but with volume units. Your units could be liters if your original number was in liters, or whatever they are. You just make it match so that they cancel. Okay, so all I have to do is take 57 divided by 3, and if I do that, I think that's 19. But it's late, and I don't trust myself. Yes, it is. It's 19, and I'm going to put a 0.0 in the end because it's got 3 significant digits in my original number. And that's the answer. Okay, so to review, we have to make a plan, and the plan is going to have to get you from whatever you're at the beginning to whatever you're at the end. So you're going to take the balanced equation and you're going to label what's given as X, what's being asked for as Y. And the problem said we had 57 milliliters of hydrogen, so that was what was given, 57 milliliters. And it asked how much nitrogen, so that was what was being asked. Okay, then because nothing changed, we were able to leave out the first and third conversion factors because they're just going to cancel each other, and use the middle conversion factor, which is the mole ratio, and we just change the units to milliliters. Okay, so let's do the second one here. We're going to use the same balanced equation, nitrogen reacting with hydrogen to form ammonia, and everything is gas. And this time, what volume of ammonia is the question mark, so that will be our Y. And we are starting with a certain amount of hydrogen, so that will be our X. And we have 6.39 times 10 to the 4th liters of it. Okay, we need to keep track of the conditions though. So the ammonia is at STP. And is that the same for the hydrogen? What volume of ammonia at STP can be produced from the complete reaction of that much hydrogen? It doesn't say anything else, so we can assume that that's also at STP. Okay, so I'm going to just try to draw a line in here, keep those two separate. Okay, so we have the same conditions before and after. We have identified what's given and what's being asked for. If you're in the same conditions, you can use the shortcut, and you can skip right across. And the only thing you need to use is the mole ratio as a volume ratio when you do the shortcut. Okay, so I'm going to start with what's given. And I'm going to take the mole ratio. This is X here. So the mole ratio would be 3 moles of X for every 2 moles of Y. But since we're in liters, we're going to, oops. Hate when it does that. We're going to change moles to liters here, and we're going to change moles to liters here. Okay, so all I need to do is use the mole ratio, because if I didn't, and I would just be doing this, 6.39 times 10 to the 4th liters. 22.4 liters make a mole of X. And then I would say 3 moles of X for 2 moles of Y. And then I would say a mole of Y takes up 22.4 liters of space. And this conversion factor would cancel this conversion factor. And so all I really need to use is the middle one. So that to save time, we're just using the middle one, and we're switching the units so that they make sense and cancel. And so I just need to take 6.39 E4 times 2 divided by 3. Which is 42,600 liters. And I wanted to have 3 significant digits, so they actually converted it up here at the answer to be in scientific notation. You wouldn't have to, because it's still got 3 significant digits either way. Okay, so again, the conditions were the same before and after, so I only need to use the mole ratio as my conversion factor and change the units to match whatever's given. All right, now letter D. It's the same reaction. Oops. Nitrogen reacts with hydrogen to yield ammonia. Everything's gas. Identify what's given and what's being asked for. So it says what volume, use green, what volume of hydrogen, so that's the question mark, that's going to be Y, at STP is needed to produce 800 liters of ammonia. And the ammonia is at 55 degrees Celsius and a pressure of 0.90 atmospheres. Okay, so I'm going to convert the temperature to Kelvin before I forget. So 8, 12, carry the 1, 328 Kelvin. Actually, just get rid of that. Okay, so our information is gathered up. We are given an amount in liters of X and asked to find Y. The conditions changed from the beginning to the end. Here we're at one set of temperatures and pressures, and at the end we're at STP, which would have been 273 Kelvin and 1 atmosphere. So we can't use the shortcut. We can't just skip over the first and the last conversion factors. So what would our plan be in this situation? Well, how do I get that 800 liters converted into moles? I need to take my volume of X, which is 800 liters, and I need to convert it to moles of X, and then moles of Y, and then they are asking what volume, so we're going to go back to liters of Y. So in my mind, it's always a good idea to kind of plan out the process that you're going to have to go through. And you're always going to have to go through moles of X to moles of Y. It's just what do you do at the beginning and what do you do at the end that you have to figure out. Okay, so we are not at STP at the beginning, right? No. So we have a problem. We can't use 22.4 liters per mole unless we're at STP. So we need an alternative. And the alternative is going to be to use the ideal gas law. So the ideal gas law, PV equals nRT, can be solved for moles. So moles would be equal to PV over RT. And once we knew moles of X, we would jump back into using the mole ratio to jump over to moles of Y. And then because we're at STP at the end, we can use 22.4 to get right here. You can use 22.4 in that spot. You just can't use it at the beginning. Okay, so I'm going to use the ideal gas law to help me take care of the conversion from volume of X to moles of X. So I plug in everything I know. The pressure is 0.9 atmospheres, and the volume is 800 liters. And because we're in atmospheres, we can use 0.0821 liter atmosphere per mole Kelvin. And the temperature is 328 Kelvin. Atmospheres, liters, Kelvin. Leaves you with moles on the bottom of the bottom, which would flip to be on the top. So that's correct algebra. So we need to just solve this for moles. So 0.9 times 800 divided by 0.0821 divided by 329 is 2.67 moles of X. Okay, now I just took care of getting from volume of X to moles of X. How do I get from moles of X to moles of Y? Well, I have to use the mole ratio, always. So what's the mole ratio between X and Y? It is 2 moles of X to 3 moles of Y. All right, that took care of that second jump right there. Now, how do I get from moles of Y to liters of Y? We are at STP now, so I can use 22.4 to get back out to liters. Okay, so I couldn't use 22.4 at the beginning because I wasn't at STP, so I had to use the ideal gas law in its place. Once I was in moles, I had to use the mole ratio to jump across, and then I can use 22.4 liters at the end. So 1 mole of Y would take up 22.4 liters because we're at STP. Okay, so I'll solve this. 2.67 times 3 times 22.4 divided by 2 is equal to 89.7. No. Did I enter that wrong? Because my answer's wrong, so what the heck did I do wrong? 800 liters. I may have put something in my calculator wrong. Times 800. Oh, this answer was supposed to be 26.7. I'm sorry. Not 2.67. That's going to be the only problem. So I would get 897 liters instead of 89.7. And it's probably just a slight rounding difference between me and whose answer is there. I don't know who she is, but yeah. Okay, so that's how you do it when you're not at standard temperature and pressure. Now I should probably do one more, so let me get the you could see my other videos there. My kids kept coming in the room and making noise, and so I had to keep stopping again. Okay, we're gonna do, let me crop this down. Okay, let's look at this one. Propane burns according to the following equation. So propane in your gas grill. Look at all the gases that are in this. So this is gas stoichiometry. We have to identify X and Y. So it says what volume of water vapor. What volume of water vapor? That would be our Y. And it's measured at 250 and 1 atmosphere. So temperature 250 degrees Celsius. Pressure 1 atmosphere. Oops. I'm going to put the 1.00 so I don't forget about my significant digits. Erase this so it's not in the way here. Okay. 3 liters of propane is burned. So propane is our X, and we have 3 liters of it, and it is at STP. Okay, so we figured out what we were given and what we were asked for. We looked at the conditions before and after to see if they changed, and they do. We can't use the shortcut where we only need the mole ratio. We have to do a 3 conversion factor problem. So we're going to figure out what our plan is. We're given a volume that's at STP. So we can use the 22.4 conversion factor to get to moles of X. And then we have to get to moles of Y. You always use the mole ratio for that step. And then the problem asks you for volume of Y, and you're not at STP at the end, so you're going to have to use the ideal gas law to get there at the end. Okay, so we need 3 conversion factor. We need 3 steps, I should say. It's actually going to be 2 conversion factors and then the ideal gas law at the end. So 3.0 liters of X. It takes up 22.4 liters of space for every 1 mole of gas. That's because it's at STP. The mole ratio is 1 mole of X for every 4 moles of Y. Move this away from this a little bit. Okay, and then we don't really have a last conversion factor because we have to stop and use the ideal gas law, so I'm just going to get this in. Alright, so 3 divided by 22.4 times 4 is 0.53. 6 moles of Y. So see, we went from here to here using the 22.4. Then we went from there to there using the mole ratio. Now we can't get from there to there using a conversion factor. We have to use the ideal gas law. So what is moles? What variable in the ideal gas law? Moles is N. So we know N. What else do we know about Y? We know pressure, and we know temperature, and we always know R because it's a constant. So the only thing we don't know is the volume, and that's what we were supposed to be finding. So we need to rearrange this equation to be V equals nRT over P. And we're just going to plug in everything. So E is 0.536 moles times R times temperature, which was 200, whoops, I have to convert that to Kelvin, 250 to 273. It's 523. And divide by pressure, which is 1 atmosphere. So 0.536 times 0.0821 times 523 is equal to 23.0. And we only had 2 significant digits in our original number, so it's just going to be 23 liters. I'll check my units: moles, moles, Kelvin, Kelvin, atmospheres, atmospheres, leaves me with liters. Okay, so that's how you do gas stoichiometry. You're going to have to get this flow chart kind of straight in your head, and it's usually not going to be dealing with particles and mass as much as the other problems that we did, but there will be some that do go back and maybe ask you to start in liters and use the 22.4 and then convert to mass at the end. And so you'd have to do maybe this path: liters to moles, moles to moles, and go back to mass. You just have to plan your route. You know, the route can be different every time. It can go anyway. So you just have to, I mean, I think this is a really good idea to write out your path. And I think you should definitely organize your information. And if you do that and you're careful, and you figure out how you're going to get from step to step to step, it should all work out. Okay, the answers are given on the worksheet, and let me see if I go back to it. I'd like you to do a bunch of these. I did basically problem 1, and then I did A of problem 2. So I'd like you to finish problem 2, and then do 3, 4, and 5. Okay, consider that to be today's classwork and then a little bit of homework. If you are feeling like that's impossible based on other work that you have in other classes, do as much as you can. I mean, I hope that you'll get through those, but I don't want you to feel overwhelmed. So I don't want you to come in and say, I don't know what I'm doing, I have no idea. There are steps you can do for every problem. You can always balance the equation. You can always identify X and Y. You can always look at the flowchart and plan out your path. So if you do those things, it just kind of guides you towards figuring out how to do it. So don't be helpless. You can do this. And I'll go over it all tomorrow in class if you are struggling. Okay?